Hello, in this video, I'll present my final year project on environmental sound recognition for robot audition. We'll have a look at the state of the art of environmental sound recognition, then at the structure of my proposed algorithm, and finally at the results that I obtained. First of all, we have to understand what is environmental sound recognition, ESR for short. Chachada and Kuo describe environmental sounds as sounds that one encounters in daily life other than speech and music. So ESR is the exercise of giving names or labels to those sounds. Much like image or speech recognition, ESR could provide a new layer of intelligence to our robots so that they can understand their environments and react accordingly. However, unlike image and speech recognition, ESR is only at the recent stage of research, but shows potential in fields such as biology, medicine, surveillance, or military. So ESR research started about 30 years ago, and much like any other recognition problems, the research has focused a lot on feature extraction and classification. In 2003, Calling City gave a first extensive comparison of techniques for their surveillance recognition problem, and they draw a clear distinction between stationary techniques versus non-stationary techniques. Stationary techniques look at the frequency present in a sound, whereas non-stationary techniques both look at both the time and the frequency present in the sound. The latter is more suited for environmental sounds as they are non-stationary in nature. However, a lot of stationary techniques exist and some very efficient, such as male frequency capture coefficients. There is also a lot of research done on the different classifiers used. So many have been tested, from cluster type classifiers, k-nearest neighbor, support vector machine, Gaussian mixture model, but also neural networks such as deep neural networks or multi-layered neural networks. Some have tried to tackle more complex challenges, such as simultaneous sound recognition or recognition of noisy sounds. However, it is really hard to compare all of those results because no standard database exists. Furthermore, there exists a huge number of sounds and therefore classes, and it is known that for a classification problem, the more classes you have, the worse results you'll get. So some have circumvented that problem using soundscape recognition, and others have limited their number of sounds to only a family of sounds. We will be doing the latter in our proposed solution for impact sound identification. We will be only looking at everyday impact sounds such as clapping, ball bumps, or keyboard sounds. We have devised a benchmark algorithm which uses stationary feature MFCC and its derivatives, along with a cluster type classifier which uses either KNN or SVM. We have also added an adaptive frame filter technique which removes any of the noisy or empty frames. In this presentation, we will be looking at the overall structure, and then I'll explain each of the parts in greater detail, and finally, we will look at the results. The project has been done in conjunction with Suzy Jaewell Yu in China, and we have worked on the paper together. And so I will present some of her results and give her due credit when they come up. First, a system overview. We can see here that there are three main parts to our system. There is the pre-processing stage, the feature extraction stage, and the classification stage. First, our impact database, made of nine classes, is divided in two parts, the training data and the testing data, which goes to our pre-processing stage to be shaped and filtered in the right way. And then the filtered frames go to our feature extraction stage, where we extract the MFCC, delta and delta-delta MFCCs. The feature vector is then sent to our classifier. The training data is sent to our model to train our KNN or SVM. The model is then sent to the classifier. The testing data is directly sent to the classifier with the trained model, and the classification process produces a label for each frame, and we compare the label to the true label, and thus we get a frame accuracy. We also get a sound event accuracy by putting together multiple of those frames which compose a sound event, and then we have a label which is the average of all those labels, of all those frame labels, and we compare it to the true label and get a sound event accuracy. Now let's go in more detail in each part. We have the pre-processing is the first stage, which is divided in two. We first have the framing stage, which subdivides our sign files in smaller frames. The frames are overlapping, which means that our second frame will start before the end of our first frame. The overlap ensures continuity between our frames and is better suited for our feature extraction stage. We then have our adaptive frame filter, which analyzes the short time energy and zero crossing rate in each of our frame and compares those values to a threshold and either keeps or discards our data. We say that it's an adaptive frame filter because we have trained an unsupervised k-means classifier to create our threshold. We have given our short time energy and zero crossing rate to this classifier, and it produces two clusters. One cluster for our voiced frames and one cluster for our unvoiced frames. Here, the purple one is the voiced and the yellow one is the unvoiced. For each cluster, we also get a centroid. And drawing the line between the centroid and taking the bisector, which is here the red line, we use that red line as our threshold. So you can see that our threshold comes directly from our data, thus being adaptive. Using that technique, we are able to reduce the number of features used by 26%, which improves our complexity. However, this comes at the cost of a decrease in accuracy of about 1%. Now that we have our frames ready, we can send it to the feature extraction stage. The feature that we extract here is the Mel frequency capsule coefficient, MFCC for short. MFCC is a stationary feature, which means that it only looks at the frequency information in our frames. It is based on the Mel scale, which is the same scale as the one in the cochlea in the human here. This scale gives higher resolution at lower frequencies and lower resolution at higher frequencies. MFCC returns a set number of coefficients which represent the amount of energy present in each filter over that scale. Here you can see the filters drawn over our frequency scale, and the MFCC would return a number for the energy present in each of those filters. We also extract delta MFCC and delta delta MFCC, which are the rate of change and acceleration of MFCC and give some indication of how MFCCs are evolving in time, which is helpful for a non-stationary sound. Now that we have our features, we can send them to our classifiers. We have tried both k-nearest neighbors and support vector machines. K-nearest neighbor is the easier to understand. I'll now start by explaining it. So k-nearest neighbor computes the Euclidean distance between our test data and all of our train points. And then for a set number of k's, it will find the k nearest neighbors to that test data. Here for k equals 3, we have those 3 train points are closest to our test data. And then we define which class the test data belongs to by vote. So here for k equals 3, we find that our test data is a triangle. However, for k equals 5, we find that it's in fact a circle. So we can see that the number of k that we choose is very significant for the accuracy that we will get. So it is important to find the optimal one, and we have done a hyperparameter analysis to find which k we should use. We have fed 7 MFCCs to our KNN and increased the k value, and found that for if k equals 5 or 7, we get the best results. And for anything above that, we have a decrease in accuracy. So we also have tried support vector machines. Support vector machines try to separate data using a hyperplane and linear hyperplane, which we say is optimal because it tries to maximize the margin between the hyperplane and the support vectors. Support vectors being the points that are closest to our hyperplane. If the data cannot be linearly separable, then we map our data to a higher dimension and thus gain linear separability. The function used to map the data is called the kernel function and can massively increase or decrease our performance. So we have, again, tried to do a hyperparameter analysis for our function and tried linear, polynomial, and radial basis function and found that the radial basis function is the one yielding the best results. Now that we have explained each of the main stages of our process, we can finally look at our results. And so here, first, we look at our overall results and find that for KNN k equals 7 MFCC, we have an accuracy of 91.8%. And for SVM RBF with 7 MFCC, we have an accuracy of 95.2%. So we have very satisfying results with SVM being better than KNN. We can have a more precise look at how each classes are recognized using our confusion matrix. And we find that the paper shuffling class, the clapping sounds and the keyboard sounds are the ones worst performing. This can be explained by the presence of noise for keyboard sounds or complex time structure for the paper class and a lack of training data for our clapping sounds. If we look at our SVM confusion matrix, all of the results are better, but the same classes have the same problems. And so we can understand that the classifier doesn't solve those problems. And it probably comes from our feature, MFCC, because MFCC is known to react poorly to the presence of noise, but also is a stationary feature, so cannot characterize any complex time structure such as the one present in the paper shuffling class. We have also done a feature analysis and tried first to find the optimal number of coefficients for MFCC, and then tried to find optimal combination of feature fusion. The table on the right is provided by Susie. First, we have done an analysis of the number of MFCCs that would be optimal for our algorithm. We have found that for an increasing number of MFCC, we have an increasing accuracy and up to 5 or 6. And then after that, we have a stabilization of our classifiers. We see that KNN reacts better to a lower dimension of features, but SVM reacts better to a higher dimensions of features at the cost of complexity. Similarly, we have also added delta and delta delta MFCCs and energy to our feature vector and found that we have a significant increase in percentage in accuracy. And again, with KNN being better at lower numbers of features and SVM better at higher numbers of features. We see that using feature fusion is highly beneficial for our system. So in conclusion, we have created a benchmark algorithm which uses stationary features MFCC along with cluster type classifiers, and which provide very satisfying results from 90 to 98% of recognition, and with a sound event recognition rate of 100%. This is a great benchmark algorithm on which we will be able to do other researches with other features and other classifiers. We have also added an adaptive frame filtering technique, which is able to reduce our number of features by 26% at the cost of about 1% in accuracy. We would need to do further signal-to-noise analysis in order to find an optimal threshold, but also to test the robustness of our system. We have also done feature fusion and found that that significantly increases our accuracy. Finally, we should do a time analysis if we want to implement that algorithm in real applications and find where we could optimize our code and how we could make it better so that it could be implemented in something like an edge application. Thank you for your time. Please feel free to ask any questions.